So for our last video in this series, we're going to take a second to talk about Riemann sums. The theory of limits of finite approximations was made precise by this German mathematician, Bernhard Riemann. Riemann sums are fundamental to the theory of definite integrals, which we are building towards, and of course our fundamental theorem of calculus. So we're going to begin talking about limits of finite sums, and a finite sum with finite sum approximations that we considered previously, drawing those rectangles and adding them up, they became more accurate when the number of terms increased, meaning we created more rectangles of shorter interval length, right? So as these subinterval lengths or partitions narrowed, the sum became more precise. And so the idea here is how small of a width can I make all of these partitions on these rectangles? So we look at creating increasingly more rectangles of a smaller width. But my question is do the lengths of these subintervals in the partition, right, do all of those rectangles have to be the exact same width? So let's look at a picture. So here we have a curve, and there are numerous rectangles drawn on this curve. But one thing you might notice is we have this short width or narrow width rectangle, and then some of these rectangles may have a wider width. So these rectangles seem to fit the picture a little bit better when they are not all of equal widths. So we're looking at dividing this closed interval from A to B into subintervals that are not all necessarily the same width, right? And we want to form a sum in the same way. So you can see I've brought a second picture in, and there are a great deal more of our rectangular shapes, right? And so what a Riemann sum basically says is that we don't have to make all of these rectangles have the exact same width or choose their height value exactly by the midpoint. We can choose it however we want. We can draw these rectangles however we'd like, and that's going to give us a better approximation. So formerly, what we did is we said that change, that subinterval length, was defined by taking your endpoints of the interval b minus a and dividing it by however many intervals you want to. But do we have to choose them that way? And the answer is no. So this will bring me to my formal sort of Riemann sum definition here. So let's define S sub p, my Riemann sum. And we're going to say that this Riemann sum, well, that's messy. This Riemann sum from k equals 1 to n can be represented by this function f of c sub k times delta x, so my change, my horizontal distance, delta x sub k. Okay, so we have a vertical distance, that function value, and a horizontal distance, my delta x. And the choices of the points, c sub k, on the intervals, they can be anywhere you want them to be. So in relation here, we're saying we could choose a specific set quantity of n intervals, all of equal width, but we don't have to. We can choose as many as we want, and we can make them whatever width we want, and we can choose this c value to be at the right, left endpoint, or the midpoint of each of those intervals. And in situations where we have regularly sized intervals, we can just make them thinner. We can make as many of these little rectangles as we want by increasing the quantity of subintervals, making n larger. So the last thing we want to talk about is, when we are creating all of these subintervals of varying widths, we can ensure that they are all thin enough by controlling the width of the largest subinterval. And that is what we call the norm. So what is the norm of the partition? And the norm is the widest of all of my varying interval lengths, right? So I've drawn all of these little rectangles. This rectangle's this wide, this rectangle's that wide. We've got all these different rectangles marking our curve. And so the widest one represents the norm. And if we can say that the norm is small, we're going to say, hey, they're all sufficiently small because the norm is the biggest one. So the norm of the partition is defined by using these double bars on either side of P. And the norm of the partition is the largest subinterval length. And so as I've said, I'll say this again, if that subinterval length is sufficiently small and it's the biggest, then everything else is going to have a very small width for their partition as well. So looking at this picture here, I might judge, and this is just by eye, but this rectangle, that width would represent the norm because it appears to be the widest length. And if I make that rectangle's width sufficiently small, then all of the other rectangles are sufficiently small. I do want to note, you'll notice in this picture, we have rectangles below the x-axis. Those would have a negative area, right? So each of those rectangles, we would be getting a negative area. So if we are trying to calculate area of the total region, we do want to keep in mind that things below the x-axis may return a negative number. We might have to use absolute value. And then also it's possible to have a rectangle of area 0, so no height. And we saw that in an example we did in our previous unit. So let's look at an example. We'll find a norm and we'll find a Riemann sum, which is just a big fancy name for making a bunch of rectangles and adding them up. So here we're going to find the partition, and we are looking at some function on a closed interval from 2 to 1, because that's where I start and that's where I end. Okay, so if I choose these as my partitions, I've got -2, -1.6, -0.5, 0, 0.8, and 1. Essentially, what we want to do is determine the widest of these distances. And we could do a subtraction on each of these intervals, but we're going to find that -1.6 minus -0.5 is going to provide us with a width. This is 1.1 unit wide. So my norm for my partition is 1.1. So a Riemann sum is just the fancy word we use to say, hey, we're going to draw a bunch of rectangles. We're going to determine the height of them based off a midpoint, based off a right or a left endpoint, or at our choosing. And these rectangles can all have an equal width, or they don't have to. And as long as I determine that the largest rectangle width is sufficiently small, all of my other ones, I will assume, which are smaller, would be also sufficiently small. Okay? So we can do this at varying widths and heights, or we can specify. And in this problem, we're going to specify. So we're going to find the formula for a Riemann sum obtained by dividing that interval from A to B into n equal notice equal in this situation, subinterval lengths. And we're going to use a right endpoint for my c sub k value. So that's how I'm going to choose my height. I'm going to determine my height off of that point on the right side of each subinterval of my partition. Then we're going to take the limit of these sums and look at what would happen as we had infinitely many sums. And we're going to calculate the area under the curve on that closed interval. So we're going to use the function f of x equals 1 minus x squared on the interval from 0 to 1. So to start this problem, I'm going to set this up. I'm going to say, all right, let's do the sum as I goes from 1 to n of 1 minus c sub I squared times some delta x, right? So I'm going to choose a c value on each interval and then plug it into my function. That's going to give me my y, and the delta x is going to give me my width, my x value. So in order to determine delta x, remember delta x, we subtract the endpoints of the interval and divide by n. So in this case, we have 1 over n. And c sub I equals I times delta x. So we have I over n. So now my sum, I equals 1 to n. I've got 1 minus, we said c sub I is I over n squared. And my delta x is 1 over n. Now, n is a finite value here. N isn't going to be changing. I is what is changing. So 1 over n would remain constant. I can pull that in front and I say 1 over n times the sum as I equals 1 to n of 1 minus I over n squared, which is 1 over n, sum from I equals 1 to n of 1 minus I squared over n squared. Now, I don't like that denominator being in there, and with some creative algebra, I can factor out 1 over n squared. I can take this guy and factor it out. So that's 1 over n squared. That goes in front of my sum. I have I equals 1 to n. So if I factor 1 over n squared out of this 1 value here, that leaves me with n squared minus I squared. So now let's break up this sum. So now I've got 1 over n cubed in the front times the sum as I equals 1 to n of n squared minus 1 over n cubed times the sum as I equals 1 to n of I squared. So I've used my difference property for sums. And I can calculate this first sum here. N, of course, n squared, that's a constant. That's not going to be changing within the context of this problem. I will be changing. So this is now the same as 1 over n cubed. That's a funny looking n cubed. N cubed, pull the n squared out, that's going to give me 1 over n, times the sum as I goes from 1 to n of 1. So that's the sum of a constant. And the sum of a constant is going to be that constant times n. So the first piece, n squared over n cubed, that gives me 1 over n. And the sum of my constant is 1 times n times. So we can see this first piece here simplifies to 1. And then my second part, if I look at simplifying this, or just zoning in actually on that sum, remember we have a formula for the sum of the first n squares. We defined that in our previous video, but that formula, the sum from k equals 1 to n of k squared, is n times n minus plus 1 times 2n plus 1 divided by 6. So this sum can be calculated. That is going to be n plus 1, 2n plus 1 over 6. We know that is true. So if I FOIL in the numerator and distribute that n cubed into the denominator, I've got minus 2. That minus should look like it's in front. Minus 2n cubed plus 3n squared plus n over 6n cubed. And I can simplify this if I divide all of my terms in the numerator by n cubed. That first term is 2. N squared divided by n cubed, I'm going to get 3 over n. And then I would have 1 over n squared, all of which is over 6. So I'm running out of space on this page. I'm going to pause, skip to the next page, and rewrite what we're starting with. So this represents the sum of my function. Remember, my function was 1 minus x squared. So if I divided that into n subintervals over the interval from 0 to 1, that's my partition. If I divide it into n subintervals, this represents my sum. And you're going, Ms. Stein, why did you do all those weird fractions in there? Why did you simplify it like that? Well, if you remember, and actually I'll leave that, that's my sum, I'll leave that in a box. Okay, we said we want to calculate the sum as n goes to infinity. So if we look at calculating n approaching infinity, we're calculating a limit. And I rewrote my sum like this because it was just going to be easier for me to calculate the limit. So the limit of this sum, we'll say thus, the limit as n, as we have infinite rectangles on this 1 unit wide width of my sum, I equals 1 to n of 1 minus c sub I squared times delta x. Well, that's going to be equal to the limit of the sum. So that's equal to the limit as n goes to infinity of 1 minus 2 plus 3 over n plus 1 over n squared, all divided by 6. So if I look at calculating this infinite limit, that means I'm plugging infinity in for n. I've got 1 minus 2 plus 3 over infinity plus 1 over infinity squared divided by 6. And both of those terms go to 0. So I have 1 minus 2 over 6 is 1/3, and that gives me 2/3. So 2/3 is the exact sum of all of those little rectangles, infinitely small in width. So we are looking at the curve f of x equals 1 minus x squared. So that's a parabola opening down, shifted up 1 unit. So it's a parabola, looks like this. Of course, we are only interested in the right half from 0 to 1. And basically what we have calculated is that that area is 2/3. So this builds towards our definition of a definite integral. And so to just recap a little bit here, a Riemann sum is a way of saying, hey, this is just the sum of the areas of all of those rectangles. And what we talked about in this video is that the rectangles do not have to be equal width. They can be varying width as long as I know that one of the rectangles is sufficiently small, the largest width one, then they're all going to be sufficiently small. And I can choose the right side or the left side. It doesn't matter where I choose that C value on each of those subintervals on my partition. So Riemann sum, fancy name for adding up the areas of all the little rectangles of increasingly infinitely small width. I hope that wasn't too wordy.